Hi everyone. Today's the lecture on regarding the motor start and direction control, which is a really important lecture when it comes for industry. And so there are different ways of starting and stopping motors. And today's I'm going to teach you how to start and stop and directional control and starting methods, basically for three-phase induction motors. Okay, before we move into that, let's take a look at this video. So this video covers the basic devices for control and protection when it comes for these motor controlling. So let's take a look at this first and we can discuss the session later.
Hi, I'm Josh Bloom. Welcome to another video in the RSP Supply Education Series. Today, we're going to be talking about motor starters and motor control basics. The primary purpose of a motor starter is to allow us to start and stop a motor safely. It also allows us to start and stop a motor from a remote location. So essentially, a motor starter is an electrically operated switching device. They are primarily made up of just a few components. The first is a contactor. The second is an overload. And they are commonly used with some sort of circuit protection. So contactors actually provide the current to our motor. Their job is to establish and interrupt power in an electrical circuit. Overload protection protects the motor from drawing too much current over a longer period of time, which can cause the motor to overheat and burn up. So let's first talk about the contactor. A contactor operates much like a relay in that when electricity is applied to the coil, it slams the contact shut, allowing current to pass through, providing power to our motor. For more information on how relays and contactors work, please see our other video. We'll link that in the description below. A magnetic contactor is operated electromechanically without any need for intervention. This allows us to operate the contactor remotely, so we don't have to put any kind of operators in any sort of dangerous situation that might be close to our motor starter. So in order to function properly, a contactor uses a small control current to open and close the contactor. Most contactors typically have auxiliary contacts as well. These contacts allow us to monitor the state of the contactor, whether the motor is actually on or off. Some contactors have multiple auxiliary contacts to monitor other types of systems in the contactor. Next, let's talk about overload protection. An overload is designed to protect the motor against a prolonged overcurrent. What this means is if the motor is running at too high of a current for too long, it can overheat and destroy the motor. How the overload provides this protection is it has a current sensing unit built within the overload itself. We have either an electronic current sensing unit or a thermal current sensing unit, depending on the type of overload that we use. So for example, on an electronic overload, we have the ability to set via a dial on the overload the amount of current that we want to allow to our motor for a specific period of time. So on the thermal overload, we have the ability to insert a thermal element to our specific application and need. So once the overload has sensed that the motor has drawn too much current for a sustained period of time, it has the ability to disconnect the current that is passing through the starter. So to meet protection needs, overloads have a time delay to allow small overloads to occur without breaking the circuit. This allows us to operate our motor without having it turn on and off frequently because of small overloads. Lastly, commonly used with motor starters are motor circuit protectors. These are essentially circuit breakers that are specifically designed to be used with motor starters. They operate by preventing large spikes in current that might be caused from a short circuit. Motor circuit protectors use a form of magnetic protection, which is specifically designed for these types of spikes in voltage. For more information on magnetic protection, please see our circuit breaker video that talks about this. We will link in the description below. Another type of protection that is used in place of motor circuit protectors is some type of fused disconnect. However, it is important that we use fuses that are designed for this type of application. So let's talk about a few things that we want to consider when we're purchasing a motor starter. First, we want to determine whether we need a NEMA starter or an IEC starter. Then we want to make sure that we match up our motor with the specific type of motor starter that we purchase. In order to do this, we need to know the motor voltage. We also need to know the motor full load amps or horsepower. And we also want to make sure we know what we need our coil voltage to be. And knowing these things, we can better determine what type of motor starter to buy. For a full line of contactors, overloads, or motor circuit protectors, and thousands of other products, please go to our website. For more information or other educational videos, go to rspsupply.com, the internet's top source for industrial hardware. Also, don't forget, like and subscribe.
Okay, so we can now see the two types of control. The first is starting with the on-site control, which means you have the motor and you have this main circuit breaker and the contactor. So this is the controlling is done locally, which means like the operator has to be sit or this close to the motor, like the control cabinet is located close to the motor. And the other one is the off-site control, which I will discuss in a few minutes. So now you can see like this is a three-phase induction motor. We have three-phase supply and with the neutral. So the so three-phase supply is fed to the main circuit breaker MCB. So you can turn on and off power to the downstream. And this is the contactor, so which causes the contact and powering up the motor. So you can use the start and stop button. So once the start button is pressed, the motor is running, and then once the stop button is pressed, the motor stops running. And the motor can be connected in either two configurations. So if this is a 6-terminal box here, so you can connect it as a delta star when you short circuit in the 3 terminals, and when you want to connect it as a delta, so this is the configuration, so I will discuss them later. And this is how it looks like a local control. You can see this is a APB dual direct online starter kit. So there's a start button and a stop button, and it's a main circuit breaker, and so after that this is the contactor. And the remote control, we have three-phase supply, and so all the control is done remotely, which means from a distance PLC. Three-phase supply is fed to a circuit breaker, and then the contactor. So the contactor is controlled by the control signals of the output port of a PLC. And the start and stop buttons could be located at remotely close to the PLC or any other control cabinet. And this the thermal overload is to protect the motor against the overcurrent. When you know, like if the motor is run with two heavy loads and the motor winding gets heated up and the current drawn is very large, and that could damage the motor winding and fail the insulation due to the overheating. Once the insulation is like insulation has insulation capability depending on the temperature, so as the temperature goes up, the insulation fails and the coils can short circuit, and so that will lead to ultimate fail of the coil. So the thermal overload is to monitor this event of overload, which is if this current is running at the motor is too high, so it will indicate to the PLC, or it can act by itself to disconnect the motor. And so all the wiring has to be routed to the motor from a remote location. So the PLC just make the control decisions and transmit, and this control is done here remotely. So this is a direct online starter wiring diagram. This is the circuit breaker. You can see three-phase supply is fed, and this is your three-phase motor. So once you want to turn it on, so you can just press it. So all the three contacts here get closed, and the power is coming from here. And this is your main contactor, right? So it has a coil like a relay. So once this coil is energized, so these three contacts get closed, and the power can flow from down from top to bottom. And you have a thermal overload relay in the bottom. So if the current is too high, this will disconnect, At the same time, there's a overload auxiliary contact, which means like indication of overload, which can be wired to a PLC to display. And if you know like there's overload happen in the motor, so you can display that one. So you have to wire it to a PLC, or you can use it for any other purpose. Which means like if this contact is open, so this normally closed contact will open, so you can take it as for monitoring. So for this contactor, main contactor, so this is a contact coil, and it is also has a auxiliary contact M1 and M2. Right, so this is this control wiring. So we can use start and stop push buttons, so momentary push button. So once you press it and release it, and push this one stop is you press and release, so it will do the job. You can see here now thermal overload. So when it is normally running, so thermal overload contact, this one, right? So it is closed, normally closed contact, no overload happens. So if the overload happens, this will open, right? In the normally, this is closed, so the current is coming from here. And the stop push button is not pressed, which means that the current can still come to here, right? This path is completed. And this is your start button. So if you press this one, when you press this one, so you close this one here, and the current is now coming to the A1 and A2 coil, like this is the neutral, right? So this is a L1, so you can take wire this to any phase here, maybe L1 here, and this one to a neutral from the three-phase supply, right? So this is how you do the wiring. And right, once you press this one, this is closed, and A1, A2 energized. So A1, A2 energized, which means these contacts will close, and the power will be flown to the motor. And the same time, when A1, A2 coil energized, so M1, M2 get energized, this contact will close. So this is M1, M2, right? Same M1, M2 here. So as this is closed with this power connection, this is like happening in a very short time. Like someone is pressing this one, and this happens, and this closes, and this is also closing, right? Which means it's self-latching now. That now the current can come forward from here. So if this push button is released by someone else, right? So this guy has now released it, but it's still the coil is energized because it is self-latch now. Like this one is closed and this one is closed, and it is keep closing. So it's a latch. And so if someone wants to stop it, he can press this stop button here. So he can disconnect this, and the circuit is again disconnected. Or else, if a thermal overload happens, like if this is overloaded with the heavy load, too much heavy load, and the current will be too high, too much current, so the motor will get heated up, and this thermal overload will sense that, and it will disconnect this valve, right? Either you can press this stop button to disconnect the motor, or either thermal overload could happen and disconnect the motor. And so you have to wait until this one cleared, overload is cleared, and settle down this thermal overloading. And you have to clear the overloading of the motor. And once the system resets, you can press the start button again, and you can keep the system running. All right, so now we can take a look at the forward and reversing of an induction motor. So this might be very familiar for you if you have learned this from the electrical machines. So in a three-phase motor, you know, like you have the motor windings, L1 and T1, T2, and T3, or WUV, different notations. But so if you want to run it in one direction, so this is the wiring. If you want to change the rotation direction, you can swap two wires. So it will the magnetic field will change the direction, and the motor rotation will be changed. Okay, so it's very easy. So if you want to change the direction, change the two connections here, right? So swap them, then you can run them in the opposite direction. Right, so this is the basic wiring of induction motor for forward and reversing. This is the main circuit breaker. You have to close this one, so in order to complete the circuit power flow to the downside. And this is that main circuit breaker, this one. Okay, and then what you can do is, let's say like you want to have forward direction, so you close this one. So this contacts will close, and there's a thermal overload happening, right? So this is a forward contactor, and this is the forward contactor, and this is a thermal overload, and this is that thermal overload, and then your wiring goes to the motor. So basically, the wiring, you can see like when this contacts closer, so L1 is connected to L1, L2 is connected to L2, and L3 is connected to L3, right? So it's a pretty straight path. And if you want to reverse the motor, you can now open this forward contact and close this reverse contact. So in the reverse contact, the wiring is done something like that. So this one comes and directly goes to here, right? So which means like L1 is again connected to L1. That is okay. In the previous one also we had the same one. L1 comes from here and comes through this one and comes returning back and goes to here. So L1 is connected to L1, no problem. And now you can see here, so this one, the L2 now comes from here, and it goes to L3, right? It goes to L3, not to L2. And this one, L3, now it is coming from here and goes from here, and now it is going to L2. So you can see now L1 and L2 are swapped likewise, right? L1, L2 swapped, while keeping it, L2 and L3 are swapped, while keeping L1 the same, which means the direction is changed. Okay. And interestingly, you can't press the forward and reverse connection contacts at the same time. It will damage the motor, right? So there should be some kind of interlocking, like if this forward contact is pressed, so we should not allow the reverse contact to be operated by someone else. If the reverse contact is operated, so the forward contact should be open, and it should not be allowed to operate it. Okay, so interlocking should be there. Otherwise, if someone press both these contacts, so it will be really damaging. And so this is forward and reverse field wiring example from ABB PER16C3 series. So this is how it comes. Like you have this, you can easily assemble a direct online starter by connecting AS contactors and P16 the thermal overload relay. This is a thermal overload relay. And you can easily assemble reverse starter thanks to our complete range accessories. VM3 mechanical interlock unit, just clip on to be between two contactors without increasing the starter line. So this is a direct online starter, and it goes to the thermal overload. And you can use this reverse starter kit. And so the forward, this is the forward starter kit, and this is a mechanical interlock, which means like if this press, this one is not allowed to press, and if this is press and this one is not allowed to press, so these are mechanically interlocked, which means not allowing the both operation of them simultaneously. So this is the forward contactor, and this is the reverse contactor, and it goes to the thermal overload, like I explained here, right? Forward, reverse, and thermal overload, right? See. And this is a real field wiring example, ABB-BER163 series. And this is what you call the AC local control, which means like the controlling is done very close to the motor. And this is a DC remote control. You can control remotely using a PLC. So the wiring is done using DC wiring. And this is for AC wiring for local control. So how this operates is like this. You have this 3-base supply comes here, and this is the thermal overload, and this is the motor. And you have two contactors, KM1 and KM2. So it is not assume like KM2 is for forward and KM1 is for reverse. And so once this is pressed, the supply comes to the motor and it is running in one direction. And when this is disconnected and when this is connected, and the more you can see now the wiring is like this, like the middle one here, right? So it is connected to the middle one, right? So which means like this wire is no change, right? So it goes from here and comes back here and connected back to the same wiring, okay? And the two wires, so this one, it goes here and comes back here and return to this one, right? So this one is connected to here, and this one, it goes from here and comes here and goes to here, right? So these two are swapped. This comes here and the red one goes here. The middle one remains the same, so the direction is reversed if you press this contactor. Right. Now the thing is like you can have this the main this is control wiring, right? Someone is pressing the start and stop button. So stop button is and the reset buttons and everything is connected to one switch here. When you press the stop, this will disconnected. That is the stop button. Now what we can see here, let's say like someone is pressed this forward or the reverse one, right? Let's say this one is pressed. Okay, so if this is pressed, you can see this is closed, right? So no one has pressed the stop button, so the power comes from here, goes from here, goes from here. KM2 normally close contact, it will be this one, right? KM2 normally close contact 21 and 22. See 21 and 22, and goes to A1 and A2 of KM1 coil. This is KM1 coil, and this is its A1 and A2 terminals. And this coil is energized. If this coil is energized, KM1 is energized, which means KM1 normally close contact will be closed. So this contact will be closed, which means like, so this guy can now release this momentary push button, but still now the power can come from here and goes from here because it is self-latch, right? So KM1 close and it's normal close contact close and it is self-latch. So this guy just press and release, so it will run in the same direction forever. So if someone wants to change the direction, so now what he can do is just reset this one for a while. Oh, stop it. So the stop button press and the power disconnected and everything goes back to normal, right? And now he can do is just press the other coil, this one. So power comes from here, goes through this one, and KM2. KM2 is this one. This coil energized, and this one 14 and 13 is closed. 14 and 13 closed. So now the current path is now alternated via this from here, because now no longer need of this push button, right? So Now the current is flowing from this path through the self-latch contact through here and going back there, and so this is closed and allowing the motor to operate in one direction. Interestingly, you can see these two are mechanically interlocked. This is a symbol of mechanical interlocked. At the same time, there's the electrical interlock, which means like you can see like in the previous case when this one is pressed, this one pressed, and KM1 is energized. So KM1 energized means you can see the KM1, there's a normally close contact, right? So it is wired here, which means if you start from this direction, this one will open, right? This one will be open, which means not allowing this to operate. Like even if this one is, someone accidentally try to close this one is open, has opened and not allowing to energize the KM2 coil, like it's an interlock. Same thing happens here. And when this side is energized, when KM2 is energized, so KM2 normally close contact put here, which means like not allowing KM1 to energize at any time because this is disconnected. When KM12 is operating and KM2 normally close contact put here and it is get opened and not allowing KM1 to energize at any cost. Which means it's an electrical interlock is also there for redundancy and for another layer of protection. Now, if you want to make it as a DC control with using DC wiring and for remote controlling, what you can do here is like you have to wire these sections to a remote location. So this section you can wire far away. So the operation will be the same. So if you press this one, right? So pressing this one, disconnect this one and close this one. Okay. So the current will flow from here to here, through here, and like that. And the KM2 will energize and the KM2 will self-latch. And now the current path will be diverted from here. And even this guy releases. So it is self-latch and keep continuing and KM2 is running. And for the other case, so if this is pressed, if this one is pressed, so this is disconnected, right? And the current is flowing from here, from here, from here to here. And KM1 is energized and KM1 will be, this contact will be closed and the current path will divert it from here and it will operate like that. Okay, it is pretty easy. So this should be wired according to following these numbers. And this is the power wiring and this is the control wiring. So you have to follow this. If you have this circuit breaker, so you have to see these numbers correctly. And when you're wiring like 14, 13, which goes to where and like that, to complete this wiring. And I have just explained the logic, but when it goes for field, so if you want to replace any contactor, if it is a damaged one, so you have to be careful, follow these numbers and like that, then it will be easy. Okay, now we are moving to the last one, the star delta connection. So before that, let's take a look at what is star delta connection of induction motor from this video. All right. So this is the starter. So like in induction motor, when you run it, so initially, if you run, so large current will draw. So the delta connection allowing higher torque, but large current has to be drawn, and it could damaging, and it could make maximum demand, increase maximum demand of the power supply, and sometimes these main circuit breakers could trigger it and turn it off. So to avoid such scenarios, like starting current is too large for the motor, so what you can do is you can run the motor with the delta connection at first. You can see this is the delta connection. So any induction motor, like 3-phase induction motor has 3 coils. So U1 and U2 is one pair, and V1, V2 another pair, and W1 and W2 is the other pair. So if you want to make it as a star connection, what you can do is U1 and U2, V1 and V2, and W and W2, all the U2, V2 and W2 can be short circuited, so which act as a star connection. So you can see here, L1 comes to U1, and U2 is connected to here, and L2 comes to V1, and V2 is connected to middle, and L3 goes to W1, and W2 is connected to here. So it is 3 coils are connected in a star way, which means 230 volts is applied across each coil, so allowing a small volt, reduce torque and reduce current. Okay, and this is used for motors above 5 horsepower, and motors below 5 horsepower you can just use a DOL or direct online starter. But when it goes for power ratings more than 5 horsepower, you definitely need to have some sort of starting method. Star delta start is one of them. So it reduces the starting current, applies to motor during the start, and also reduces the disturbance and interference on the electrical supply. So when a large current flows at first, it is really disturbing to the main supply, and there could be so other circuits, the power, you can see like the lights get dimmed and likewise, so it is not good. And this is how you're going to make it as a delta connection. So U1 is connected to L1, right? So L1 goes to U1, and U2 now goes to W1, and W1 is connected to L3. So U2 goes to W1, and they are connected to L3. And V1 goes to L2, and V2 goes to L1. That's clear. And L2 goes to W2, and making it as a delta connection. So when it is delta connection, line to line voltage is 400. So full voltage is applied across the coils, allowing a large current to be drawn. So this is not good at the initially. So initially you supply with make it as a star connection. Then you switch to delta connection once the motor reaches to full load. Once it is reaches to steady state and full speed, you can connect it to the delta and make it the torque for what is required. And to achieve this wiring, so manually you can't change the wiring, right? So you can't go and unbox the motor terminals and wire this, and it is like a pretty stupid thing, right? So you need to definitely have this kind of contactors to perform this task. So you have to have this kind of 6-terminal wiring box of the motor in order to achieve this. Like if the motor is running with 3 terminals, you can't do this operation, because motors less than 5 horsepower typically comes with 3 terminals. You just plug and play. But this kind of high horsepower motors, you always the terminal blocks has 6 connections. So the user can use it for this kind of application. Right. So this is how it works. So this is your main circuit breaker, and this is the main contact. So you have to close this guy, right? So once this is closed, this is closed, and this is closed. Then so the first thing is to run this star contactor. So someone has to press this star contactor. So it is closing all these contacts, which means so W2, V2, and W3. So they are all short circuiting together. You can leisurely think about how it is short circuiting, like literally it's short circuiting likewise, right? V2, W2, so everything will be short circuited if you press this one, right? So it is short circuiting all this terminal. So allowing the motor to run in this star manner. And once the motor reaches to full load, so you disconnect this one, and press this delta contactor. So both cannot be pressed simultaneously. There should be some interlock and safety procedure as well, right? So once it reaches to full load, this delta contact is closed, which means so L1 comes here, and it goes to V2, right? L1 comes and goes to V2, and the other one down, L2 comes here, and it goes to W2. L2 goes to W2, and the other one is L3. It goes to U2. L3 goes to U2, right? Likewise, it's making a delta connection. So the circuit is completed now. So once it reaches to full speed, you can run the motor with the delta configuration, so no issue will happen. So if you want to restart, again, you have to go with the star connection, then switch back to the delta connection. Okay, now this is a field wiring example with ABB BEY16C3 series. So you have your main contactor, and so you have your main contactor, and you have your star delta connections, and they are interlocked. And this is the timer that I'm talking about, right? So the timer, you can adjust the timing. You can set the time for connection, make the star delta connection, and finally it goes to the thermal low alert, and then goes to the motor. Okay, this is that the final wiring diagram. So even though it is a star delta, so someone has to wire for one direction. You can't change the direction with this setup, right? So either you have to have this wiring, so it is run the motor in this direction, and you can switch to star delta. If you wire in this way, the motor will rotate in this direction, and you can do the star and delta connection. But you cannot change the directions with this ABB BEY16C series. It is only allowed to change star to delta for running a one direction only, right? So assuming we think about this is our wiring diagram. Like the only change here, you can see like W1 is connected to W1, and W2 is connected to this one. So this is a common, and these two V1 and U1 are swapped, which means like the direction is changed, how they have achieved the direction. think about this one first. So we are running the motor in this direction. And so this is your, we have this 3 contacts. And so the KM1, so someone has to press this one, right? So this is the start button. So this is the stop button. So if the stop button is pressed, so the power to the bottom downstream will be disconnected, and this is the start. Someone press this one, start, right? So the current will flow from here, and go to A1, A2 of the timer coil, right? KT is the timer coil. You can see this is the timing diagram. A1, A2 is this coil, right? So once someone press this one, A1, A2 energize, and at the same A1, A2 energize means this is the period, right? So A1, A2 energize from here, and at the same time the pins 17 and 18 related to this timer will close. This is 17 and this is 18, and this contact will get closed, right? See, you can see now this 17 and 16 has to be operated along with the A1 and A2 up to this period point, right? So 17 and 18 close, and the current will flow here, and the KM2 will be energized. So the KM2 is this one. So you can see now it is short circuit in the 3 terminals, and the motor is runs with the star connection. So the motor is run with the star connection initially, 16 and 18 close. KM2 coil is energized. At the same time, we can see like KM2 is running. This is opened. Okay, this is opened, and so you can see like the KM2 energized, and this is opened, which means the interlock has happened, which means not allowing KM3 to operate at any time. This is opened. At the same time, KM2 is closed, which means this contact will close. So the now current has now another direction. It can flow from here, here, and through here back to KM1. So KM1 is also energized. So this coil energized, which means this is closed. So when the KM1 is energized, this is closed. So it is self-latch, which means now the current, this guy can release its momentary push button, but this current flow will continue from this path through here, through self-latch KM1 coil, and here. So this guy is always turned on, and this one is opened, and this one is closed. So the star operator connection is happening. So after certain period, so after this T1 adjustable starting time, so the user can adjust this T1 time for the run of the motor for the star connection. And after that, there's a certain dead time or transition time T2, like which is around 50 milliseconds. That is a very short period, right? So during that period, the restart happens, which means like everything is restarted. 18 and 17 and 18 get opened, right? You can see like 17 and 18 no longer will be operated, right? So this path is opened, which means KM2 is opened. This is opened, right? And KM2 opened means like this now can return to its normal version. Like once KM2 is not operational, so it's normally closed contact. The previously it was open, now it is get closed because this is resting position. And after this transition time, 17 and 18 get operated. 17 and 18 after this, right? This is 17 and this is 17 and 28, and this path will be closed. Now the current can come from here through here, and KM3 is energized. This is KM3. Once the KM3 is energized, this one will be open, so it is interlocked, which means no one can connect it back to the star connection. This is interlocked, and so it is now back to the star connection. So this is completed, means like you can see the wiring diagram, reference to the wiring diagram. So it will become a delta connection. You can draw this and see how it connect as a delta configuration. So then now from while KM3 is energized, so the delta connection is completed, right? KM3 is energized. So the motor will run with the delta connection until someone reset or stop by pressing this one. Okay, so that's how you do this star and delta connection using a timers, and this is one simple example using ABB series star delta contactor. So different manufacturers has different ways of doing it, but this is the most practical or common one. So if you understand this, you can understand any other star delta starter pretty easily. Right, so the auto transformer start is another method of starting an induction motor with reduced torque and reduced starting current. So an auto transformer starter allows to start a squirrel cage motor with a reduced starting current, as I mentioned, allowing a reduced voltage within the acceleration duration. So in the star connection, we know like the 230 is applied, but in the auto transformer, there's a tapped connection. So it's like you can adjust this auto transformer tapping and set this voltage to a desired level, right? Unlike this star delta wiring, this auto transformer starting method needs 3 wires and 3 terminals on the motor. So you don't need to access to all 6 terminals, or you just need to have only 3 terminals from the motor, unlike the star delta method. And it simplifies the wiring from the motor, but this might be a little bit, this has to be wired somehow. At the starting point, the motor is wired to the auto transformer taps, the starter connector KM3. So initially KM3 is shorted. Right, KM3 is shorted. So the thing is now the current it makes this transformer, and whatever the voltage applies to the motor, and then the contactor KM2 is closed. So this one is closed. So now you can see like the 3-phase wire comes here and make like a transformer connection and like a voltage divider. And this voltage, like there's a voltage drop here and there's a voltage drop here. And this voltage from here to here will be applied to the motor, right? And the rest of the voltage is dropped across the transformer coil to this side. So but while changing the tapping, you can change this desired voltage. And once the motor reaches to full load, what you can do is just open them like the auto transformer generally equipped with 3 taps each phase under the adapter of the starting parameters to fill the requirements. And when the motor reaches to 80 to 90% of nominal speed, the star contactor opens, and then the line contactor KM1 is making the auto transformer contacts opening. And this starting process is done without any interruption. So after the certain period, so you can just short circuit this one, KM1, allowing full voltage to pass through the motor, right? So KM2 could be temporarily disconnected, and yeah, So these two could be disconnected, and you can complete the whole circuit, and all the power goes to the motor directly once it reaches to 80 to 95% of its rated speed. Now, as you know, like there are some motors called slip ring motors. They have this rotor also has some winding, so you can use this winding to speed control. Right. So three kind of contactors are used to control three-phase slip ring motors. Start contact, stator contactor. This is the stator contactor. So you don't need to worry about these the motor winding from outside. Like this is you just connect it to the main supply. This is the rotor. So rotor has also wiring. So you take the rotor winding outside. And initially, so if you want to start the motor with very low current, what you can do is increase this resistance, right? Resistance, like this is a three coils. They are connected in series with R2 and R1 and making a shorting at the end with these resistors, right? When the resistance is high, the current going through the rotor winding will be low, and it reduces the torque and reduce the starting current. So initially you apply, you don't do anything, right? Which means R1, R2, and every resistance is applied, which means it's run at the very low current. And after some time, this acceleration contact is closed, right? So which means this R1 and R2 and R3 are short circuited, right? So it doesn't matter if these resistors are there, because once you short circuit with a piece of wire, this resistance doesn't matter, right? So now only the R2 is applied, so the resistance reduce. And finally, once it reaches to full speed, you can short circuit these contactors, which means again short circuiting here, so R2 doesn't affect, right? So now no resistance is applied, the rotor winding is short circuited. Okay, as a summary, we can watch this video. So that will give you a brief insight what we have learned today.
As automation engineers, we write logic programs for PLC and DCS systems that monitor process variables, open and close valves, set control loop modes, and start and stop motors for pumps, compressors, and conveyor systems. Most digital outputs on control systems operate on 24-volt DC or 120-volt AC. So how do I start and stop three-phase 480-volt AC industrial motors? The simple answer is by using a motor controller. Many types of motor controllers are available, and the various types and styles all have specific uses in industrial control. All motor controllers are designed to keep the motor from being energized until the controller is told to activate. Once activated, current can pass to the motor, which energizes the motor windings and starts motor rotation. Activation of the motor controller is typically accomplished with an electromechanical device built into the controller, also known as a contactor. Other methods can also be used. Motor controllers are also referred to as motor starters. These devices are most often offered in a single unit with circuit disconnecting means, a contactor or other type of motor actuator, circuit overload protection, and motor overload protection. Motor controllers can be grouped by starting method and by starter type. Motor controllers can be classified by starting method. The first starting type is the full voltage non-reversing motor controller. As the name implies, when the controller's single contactor actuates, this motor controller type, also known as FVNR, allows the full line voltage to pass to the motor. With an FVNR motor controller, the position of the line phases is fixed, and the motor can only be operated in one rotational direction. An FVNR can be thought of as an across-the-line controller. In a full voltage reversing motor controller, the controller has two separate actuating states, one to operate the motor in the forward direction and one state to allow the motor to operate in the reverse direction. This is accomplished by adding a second contactor. The forward contactor acts the same as in the FVNR, and the reverse contactor swaps the position of two of the phases. This reversal of two phases causes the magnetic field in the motor windings to be reversed, causing the motor to spin in the opposite direction. Special physical safeguards are in place to prevent the actuation of both contactors at the same time, which would be very damaging. The third type of motor starting method is called reduced voltage starting. Large motors can have a very high starting current that may be harmful to the motor or the motor controller itself. To limit the amount of starting current to these motors, this type of motor controller applies a reduced voltage to the motor when it first starts. There are several ways to accomplish this, such as auto transformer, star delta, and soft starter. These will be described later. The last type of motor starting method is multi-speed. Multi-speed motor controllers use solid-state or transforming means to allow motors to be controlled at different speeds. Two of these methods, variable speed drive and two-speed control, will be described later. Now that I've described the four major categories of motor controller by starting method, I will now describe the six major motor starter types. The first is manual motor actuation, which requires an operator to switch the motor on and off. Due to safety considerations, manual motor starting is limited to motors of 10 horsepower or less, but they can be used on single or with three-phase applications. Magnetic motor starters, or direct online starters, are the most common single-speed starter type. For magnetic starters, a PLC digital output, a push button, or a selector switch is used to pull in a coil, which magnetically holds the starter contacts closed, allowing current to pass to the motor. Magnetic motor starters are used with FVNR and full voltage reversible motor controllers. Auto transformer motor starters are commonly used in reduced voltage starting applications, especially with large motors. When the motor starts, two contactors pull in. One of these contactors energizes a transformer circuit, and the other forces the transformer into a star configuration. The tapped output from the transformer is connected to the motor leads at the start. Once the motor reaches 85 to 90% of full voltage, the star contactor opens, and the transformer then acts as a choke to limit the voltage and the current to the motor. The main contactor then closes, and the motor controller acts as an FVNR with full voltage to the motor. Star delta reduced voltage motor starting is related to auto transformer starting, in that three separate contactors are used in the motor control scheme. In star delta, the motor is started in the star configuration, which starts the motor at about 1/3 of the rated full motor current. After the motor spins up to near full speed, the motor is switched to the delta configuration for continuous running. Make sure to check out our previous video series on this topic. We'll add the link to the playlist in the description below this video. Soft starters are another method used for limiting starting current. Soft starters use solid-state electronics to limit the startup voltage and current. With a soft starter, the voltage is gradually increased during motor startup. This allows the motor to slowly accelerate and gain speed in a controlled fashion. A variable frequency drive, or VFD, is similar to a soft starter, but allows the speed of the motor to be varied by varying the frequency of the output to the motor. Because the voltage is also regulated in the process, the startup current is also reduced with the use of a VFD. This video has provided a brief overview of 4 types of motor controller starting techniques and 6 types of motor starting devices. Whether a full voltage across-the-line motor controller is required, or a motor controller to provide a reduced voltage at startup, there is a motor controller that allows safe, efficient, and controlled starting for every application type.
Okay, so that's the end of this lecture. So if you need to learn more about this contactors and these wiring diagrams, you can refer this ABB main catalog. So all the circuit diagrams are imported from there, wiring diagrams. So you can literally see this and you get more understanding. So that concludes my lecture. So thank you for coming today. And this is all about this motor starter and stop control.